Okay, so this assignment E2 that's sort of due this weekend. A common question that comes up when doing the first part of it, the fisheries one, is this is a little different that you're setting the initial condition of the fish, the fish population, to their carrying capacity. So you've sort of already assumed that they've come to carrying capacity, and at the start of the simulation, you're saying this is day one that ships have arrived on the fishery. And so as a consequence of that, you're going to end up getting, if you implement it right, then what you'll end up getting here, let me just maybe make a blank screen. Can I do that? Yeah, there, white screen. And then let me just draw on this a little bit. All right, so normally when you guys were looking at the fishery, we would start at a very low initial condition, like one fish in the fishery, and we would watch it do a logistic growth thing where it would eventually kind of be S-shaped, and then it would reach carrying capacity up here. Here, I'm asking you to start the fishery with where the fish stock starts at the carrying capacity. So it's going to start at 4,000 here. And then again, this is like at day one, we just added in all those ships. So the fish have been sitting here humming along at 4,000 fish, but then suddenly there's ships that are in the fishery. And so they start creating an outflow because they start harvesting fish. And as they start harvesting fish, the fish regeneration rate starts to go up because there's less fish, so the remaining fish can find more resources, and eventually it comes to a new equilibrium where in the sustainable fishery case, they're going to be taking out, let's say, 100 fish a year, but then there'll be 100 fish a year regenerating. And so you end up getting a curve that looks different than all the other curves you've seen, something that looks a lot more like this. So if you build it correctly and hit sim and then only plot the fish population, you shouldn't expect to see something that looks like this S-shaped growth curve. The right curve that you should get out should look something more like this, where the fish population will start at 4,000 and then it'll decrease and then it'll come to some stable point. It'll be flat after that. And because you've got sliders in there, you'll be able to change the number of boats as well as the number of fish that each boat is able to catch. And what you'll see is if you move, let's say if you slide the slider for catch per ship to make it lower, so each fish catches less per ship, then each boat catches less fish per ship, then this line will go up closer to 4,000. And if you go higher so that each boat catches more per ship, then this steady state line will get lower. Now, eventually you'll hit a point where they're overfishing and it's not sustainable anymore. And so this curve will change from being one that looks like this to one that may start looking like this, but then will plummet and go into negative numbers because our math doesn't prevent us from getting anywhere negative. So it'll just kind of plummet like that. And that switch from a flat line to a continually like negative line is the switch between sustainable and unsustainable. So that's what you're expecting to see in that part one. So this is a little bit different. This part one here, this is the graph down here on the bottom half of the slide you'd expect to see. So, and then part two was the kind of toilet tank model one, where I've basically given you the drawing of what you're supposed to put out there. You just have to come up with different formulas for that flow equation, where the flow equation is a delayed version of the desired flow. And so that's where you're going to swap in the code for the fixed delay, for the smoothing delay, and for the third order smoothing delay. So you're just going to edit that formula, run it, edit that formula again, run it, edit that formula again, run it, and then compare all three of those. That's basically what you do for the second one there. So, so I know there are some questions there. So before we go on to the next thing, are there any general questions about assignment E2 that maybe all of you have that you want to bring up now? Otherwise, you can, yeah.
I noticed in part C of the first chapter, it only says to use a slider to adjust sips at sea. I don't see anything about this.
The catch per ship. I forget which slider asked you to do it. So if it's the same thing. If you increase the ships per sea, as you slide that ships per sea up, then this equilibrium line should go down. As you slide the ships per sea the other way, it'll go up. And as you slide it to more and more ships, then you will eventually hit a critical number. So let's say it's 36 ships, and it'll be like, what, 35 ships, it looks like this, and at 36 ships, it looks like this. So that tells me that 35 ships are the maximum number of ships I can have for this fishery to be sustainable. And at 36 ships, it's overfished. All right. Any other questions, even from online, about assignment E2? Okay, great. All right, so that's due this weekend. And so today, let me get rid of that. Okay, good. So today, there's only 2 homework assignments left, assignment E2 and assignment E5. After that, then those are sort of, aside from the reading assessments, there's no other credit really for the class until the final project. So you'll do this assignment E2, which has that bonus question on it, assignment E5, which also has a little bit of bonus. So if you're looking to make up any points in your assignment category, these 2 assignments are great ones to capitalize on that. There are no other homework assignments after these 2 assignments. But again, there are 3 chapters that we're finishing up on. So we've got, and each one of those has got the perusal, the reading assessment, the reading exercise. But then otherwise the only other kind of homeworky sort of things is the final project. And so capitalize on these, especially if you're looking to make up some credit in this category. All right, so assignment 5, this is motivated by, let me get rid of that box across the top here if I can. Okay. So assignment E2 gave you an opportunity to play with some of the more advanced features of Vensim or Insight Maker, whichever one you'd like, delays, sliders, etc. And so in assignment E5, we're going to try to have you build a more sophisticated model where I kind of give you the recipe for almost everything in it. There's a couple of things you have to figure out on your own, but this is supposed to kind of emulate the same kind of scale of model that you would expect to have on your final project. And this is motivated by that EasyJet example that we had in the last lecture and we talked about in the chapter. So if you remember there, in EasyJet, they basically said, we want to model a company that wants to maximize its growth rate. And so they built kind of a growth loop here. And this company doesn't exist in isolation. So they started out with sector 1, this kind of just the company itself. And then they said, we have to add on a sector 2, the rivals, and sort of a very basic model of their rivals. And then from there, they connected those 2 together after they built them. And then just to make it a little bit more realistic, they embellished and added a couple of other kind of complicating processes on top of it. So they're kind of more like, basically 3 parts. You build one sector, you build the other sector, you connect them together, you build maybe some embellishment across the top. And this is the causal loop diagram version. So then the to-do then is to then implement each one of these things. And usually by breaking things up into sectors, it's easier to implement this stock and flow diagram, and then this stock and flow diagram, and then connect them together. So that's kind of what they did in that last chapter. And so what this assignment is doing is kind of motivated by that. And so it's kind of a contrived case. It's not really a great model for what it is, but it's just sort of giving you an idea of how the process might work. I didn't want to take off the table a good model, so I came up with one that was kind of like, it's got a lot of flaws in it, but at least I think shows the process. And this is an idea where I just sort of, it's kind of a coupled population and municipal water dynamics model. So we're going to basically have a sector where you're building population dynamics that are based on water availability, and then another sector, which is water dynamics based on population use, and those 2 kind of connect together. And so the way this assignment's going to work is the first part, you build the kind of population here. So you're going to start with a really simple birth-death model, and then you're going to add kind of a network of effects that affects the kind of population of your city. And then in the second part of the assignment, you build a water supply sector. And that's going to have sort of these 2 stocks where you've got treated water and treated water gets used by the population and becomes untreated water, wastewater, and then has to then be treated to come back to be treated water again. So you've got this thing that's cycling around here. And then so those two sectors depend on each other. So after you've built those, then you can connect them together. And that will then be talked about in the assignment. And then the kind of bonus to this assignment is then if you can think of adding a couple of other embellishing things that would make this even slightly more realistic, then you can add those things on there. So that's the basic structure of what we're going to do with this assignment. And this assignment kind of has a recipe for how to go about doing this. And so yeah, the other bonus option here is to go and find data and document what data you have. So there's kind of two little bonus opportunities on this one. So that's kind of the basic idea here. What I'm going to talk about in this lecture is just give you some things on the front end to help you with some of the parts of this assignment that are still free form. Most of this assignment, like I said, if you've looked at it, it's like a recipe. Like it's got steps by step. You just follow. You build this, you build this, you build this, you fill in this, and occasionally you get into this point where it says like, come up for a formula with this, and you have to come up with that based on what you know from our past models we've seen, and some of the stuff that I'll kind of remind you of here in the next couple of slides. So that's kind of basically where we're going. Any questions? All right, so the basic thing let's start on first here is we're gonna have to build this population model, and I'm gonna give you data in the assignment about like average lifetime and birth rates and things like that. And you want to sort of build a realistic birth rate here that acts continuously over a lifetime. So I might tell you that on average, every couple in a population on average has 2 children. And you have to interpret that. And you have to say, what does that mean, has 2 children? And you have to remember your birth rates act continuously over the whole simulation. So you can't just go into the birth flow and say, we want 2. So like, if I were to say like the average per person birth rate was 2 children, what I'm really saying is that's 2 children per year per person. So that would mean every person in the city every year is popping out 2 new children. And so that obviously is a misinterpretation of that stat, saying the average birth rate is maybe 2 offspring per couple. So I have to say, well, how do I build a birth rate that actually makes sense based on that? So then I have to think of what piece of information do I need? Well, so like I said, this isn't really realistic. It's too fast. So really, I want maybe 2 children on average for life is probably, so really I want 2 children for life, not 2 children every year for life, right? Because it's way too much. So, and then also the other thing I need to attack here is not every individual produces offspring. So there's going to be people that don't have offspring, but there's also maybe going to be population things that have to occur. Like, for example, maybe it's not 2 children per person, maybe it's 2 children per pair. So I have to consider those sorts of things. So how do we come up with a more realistic formula? So I have to list my assumptions and let the assumptions drive the formulas for me. So if I look up here, I can say, well, I'm going to make an assumption that humans form pairs to produce offspring. That's one assumption. And I'm going to make an assumption for the purpose of this model that every pair produces 2 offspring over a lifetime. Now, there's going to be problems with that assumption, but I'm just going to start with that. And we'll talk about the problems here in a second. And then I'm going to also make the assumption that every pair lives about 70 years. And so those 2 offspring are going to be kind of spread over those 70 years. So the problems with these assumptions, for one, it's assuming, that every pair is going to produce offspring in a particular way, and maybe every pair don't. Maybe every pair, so like assuming that sexual reproduction of every pair isn't necessarily realistic if I want to model the real population. There could also be a lot of demographic differences in, some groups might on average have 4 children. Some groups on average might have 1 child. So I have to kind of deal with that when justifying these assumptions. The lifetime, there might be demographic differences in lifetime. Some groups might live less than 70 years. Some groups might live more than 70 years. And then, this idea that there's only 1 pair for the whole life, then that's also probably not realistic. So the question we always have to ask, all models are wrong, but some are useful. For the purposes of the model that we're building, how different is this from reality? And so if I were to try to make this a more realistic model, how different would the outcome be? And so I might decide that at least to get things going, I'm going to start with this as my kind of nominal model, and then I could potentially enhance it with more realistic numbers later. But at least this is more in the ballpark than just saying two offspring per person per year. That's like way too high. So now all I have to do is then turn this into a formula for birth rate. So this is it kind of broken out here. It's just doing a unit conversion like you might do in chemistry class. So ideally the birth rate is going to be in children per year. How many new individuals do I produce per year? So I say, well, I know there's 2 children per lifetime per pair. And so lifetime and pair, I need those to go away to be kind of really, I need this to be replaced with children per year. So I can say, well, what is a pair? A pair is 2 people. So I'm going to multiply this thing by 1 divided by 2. So there's 1 pair per 2 people. I did that because I am trying to well, we'll see how these cancel out when we put this up here. And then I can say, well, then I also want this, what is a lifetime? Well, lifetime is 70 years. So I would like to swap out, I'd like to cancel out the lifetime of the 70 years. So if I rearrange this in a little bit more, in a little better way here, then, so I'll go back to the previous slide. Then what I'm seeing here is this is the original 2. This is 1 divided by 2. That's 1 pair per 2 people. And then this is 1 divided by 70. And that's kind of like 1 lifetime per 70 years. So here I've got, this is 2 per pair per lifetime. Well, what is a pair? Well, 1 pair is 2 people. That's where I got the 0.5. What is a lifetime? Well, 1 lifetime is 70 years. That's where I got the 1/70. So when I do all of that, then I can end up getting 2 children per person per year. So that's the kind of unit. So if I go back here, and it's, at least from my angle, it's a little hard to see all of this, but we can see that this 1 is the 1/2 that gave me my 0.5, and this is the 1/70, and this lifetime in the numerator canceled this lifetime in the denominator. This pair in the numerator canceled this pair in the denominator, so that I ended up being left with children per person per year. And that's how I got this expression here, which in the end, this is just going to cancel, right? I mean, 2 times 0.5, that goes away, and it's just a 1/70. So 1/70 is a lot smaller than 2. And so, but this is again a little bit more realistic. And so the units here again, children per person per year. All right, so so this is going to go into this births flow where I'm going to have this average per person birth rate times the current population. And that will tell me how many births are being added to the population each time. So that's my flow rate into the population. And this is just expressed in children per year. So this was children per person per year because I multiplied it by population. I just got children per year. So any questions on this, how we got this expression? So I could give you a little bit of this data up here, these data up here, and then from these data with some unit conversions, you can come up with a flow rate in the right units, children per year. Okay, so that'll be one of the things you'll do on the assignment is to use, and you don't have to use this expression, but whatever expression you do use, you'll have to kind of justify it. It's fine if you use this expression. All right, so that's the first thing that you'll see on the assignment, first potential stumbling block. All right, so then the other thing, don't forget about DT. So in this assignment, there's going to be functions that you use that will really require making sure you get your DT right in order for the simulation to work. And likewise, really in any complex simulation, you're going to need to make sure you never forget, like you don't want to leave the DT at its default value. You're going to definitely need to dial that thing down and then maybe bring it back up if things are running too slow. So remember, just for, if you haven't paying much attention to this, it's under model settings. So in Vensim model settings, and then in the time bounds tab, you can find this time step, and that's where the DT is. If you're using Insight Maker, it's a similar thing. you go up to the settings in the toolbar. There's a little settings button, which brings up a similar settings here. And you can then set up your time step down here. And don't forget about your time units as well. So if nearly everything in your model is in seconds, you should probably set your model units to seconds. Nearly everything in your model is in years, you should probably set it to years. So, so that's, yeah, make sure you check the units, which is also on the same page in both Vensim and Insight Maker. Okay. Now, something that might even help you with the current homework, lookup tables. So you will have to build lookup tables on this one. So just as a reminder, so like this is the lookup table that you actually kind of use on the homework, the fish density one. You create an auxiliary variable in Vensim, and you make sure to set the type to auxiliary and the subtype to lookup. Don't set the type to lookup unless you know how to use. That's a more advanced way to do lookup tables in Vensim. But it's for the purposes of this class, they're equivalent to this. And so this is kind of the more straightforward way to do it in this class, where if you want to do a lookup table, remember the type stays auxiliary, even though there is a lookup under there, the subtype changes to with lookup. And that's how you get your lookup table in there. And then from there, you have something going into your auxiliary variable, in this case, fish density, and you can then put it up here as the equation, and that's kind of the input to your lookup table graph. So make sure that you've got that filled out there. And then you can go and click on the as graph and draw your lookup table. And this is something that you have already had practice doing again on the current assignment E2. And you can just put all those points in here, either manually or by clicking through the graph. So that's lookup tables in Vensim. Any questions on the Vensim side? Yeah.
Like we were showing auxiliary, is that on a specific like stock or variable?
Oh, this is on. It isn't for stocks. It's just for the like the button says A. It's anything non-stock can be configured this way. Technically, a flow could be considered this way, but you would normally just do it as a variable. So any variable, you drag that variable in, then you hit the little f of x to get to its equations, click on that, that will pop this up. And then the default will be auxiliary, most likely. And then you can then change the subtype to with lookup, and that will give you the as graph. Yeah. Question? Okay. So yeah, the as graph doesn't show up until, I don't think it shows up until you do with lookup there. Yeah.
So then you just press OK and then the graph show up?
So if you click the as graph there,
Oh, click as graph.
yeah, you click as graph, and then this shows up. And that allows you to put in all these points, either with your mouse on this or by manually typing them in down here by using this new. You can say, I want a new point, and then you can add it up here. You can delete these points. Make sure to set your X and Y min and maxes so that the graph is showing the whole range. Okay. This isn't the lookup table you'll use on this homework assignment, but it's the one you've been using on assignment E2. Is that all you need to see on this one? You asked if you guys, yeah, okay. Any questions online? Any other questions here? So after you do that, you're going to click OK down here, and it brings you back to the auxiliary variable, and it has now summarized your lookup table in this ugly format down here. You don't have to do anything with that. If you do this a lot, you start learning how to read this, and you can even start typing this in yourself without actually going through the graph part there. So you can kind of confirm that all the points you typed in are there, but you don't really have to worry about that. Once that's in there, then you can go ahead and click OK. And then in Insight Maker, it's a similar deal. So if you're using Insight Maker, lookup tables, you go into the add primitive, you go into the add converter. That's the converters are where they store their lookup tables. It'll give you this different shaped thing here. And from that new converter, you can open up the right-hand panel. When you click on it, it'll populate things on the right. And it's got a bunch of settings here. And so if we focus on those settings, if I set it to linear, then it works just like the Vensim lookup tables, where if I put in a bunch of points in the lookup table, like if I hit the little equal sign and I put in all these points, then it draws straight lines between all my points, exactly like Vensim does. But if I instead change it to none, Then I've got all my points that I put in down here, and it holds them until the next point. So it just draws a lookup table a little differently. And so Vensim doesn't give you this option. So in Vensim, if you want something that looks like this, you have to manually put in every corner, whereas Insight Maker just kind of gives you a shortcut. So that's lookup tables in Insight Maker. So I don't know how many people are using Insight Maker, but any questions about that? Okay. All right, so both Insight Maker and Vensim have got shadow variables. There will be an opportunity to use shadow variables in this assignment E5, so just a reminder of that. So in Vensim, and by the way, I put a comment online. If your Vensim doesn't have these words under the toolbox and you want them, you can go under Tools Options and then go over to, I think, Toolbars, and you can turn on those labels. And I put an announcement out there so that you don't have to go by just the icons here. So in the older versions of Vensim, they made those words show up by default. The newer versions of Vensim, they got rid of them. I think it's kind of annoying because I think they're helpful, especially when you're learning this, but so that's how you can put them back. So there is a shadow variable here. And so in the new versions of Vensim, there's actually going to be two boxes that both kind of look like shadow variable. If you don't have the words underneath them, if you mouse over them and let the mouse sit there for a few seconds, it'll pop up a little context box that'll say, make a shadow variable. And if you click on that, and then you click where you want to go, then it will then bring you a list of possible shadow variables, or otherwise known as ghost primitives in Insight Maker. And these basically just give you a copy. They either allow you to pull out a variable like time that the simulation has access to, but you hadn't had access to in your diagram, or allow you to create an alias to other variables that are on the canvas elsewhere, so you don't have to create wires connecting that. So this looks really nice for sectors, because you can draw sector 1 up here, you can draw sector 2 down here, and instead of having long wires connecting the two of them, you can create shadow variables locally that they can wire to, and they end up connecting across your whole canvas, but it doesn't have to create this kind of like extra loops that you see around here. So it's just a way to clean things up. So yeah, so they give access to time as well. So in Insight Maker, I don't think I went over this earlier, but under add primitive, they've got a ghost primitive, and it's the same idea. So you can you can select an object, and then you can say add primitive ghost primitive, and it can create a copy of it. And it actually looks just like the original one, but it's kind of faded a little bit. And then you can drag that and place it anywhere around here. And whatever happens to this one will also happen to this one. So if you draw links to this one, you're effectively drawing links to this one and vice versa. So same idea, you can do ghost primitives in Insight Maker. Yep.
So if you made something in ghost primitive, but it was just supposed to be regular stuff, would we get things off that?
Well, no, I mean, so you can't make a ghost primitive unless it already exists. And so the stock already has to be on there, and then you could create a primitive to the stock that's like a copy of it. But it's like, yeah, you can't be a ghost unless you were once alive. Okay. All right. Any other questions about that? All right. Good. Okay. So then the other thing, so then time functions. So this will be more for those of you in your final, so this won't be something we necessarily use in assignment E5, but occasionally we get final projects where people want to simulate seasonality. So if they're simulating like energy use in a city, for example, you might want to show that there's a lot more energy use in the summer. So you might want to simulate 10 years worth, and every summer you want high energy, but you don't want that high energy to stick around in the winters of each one of those years. And so, so these time functions, there's a particular way we can simulate this type of kind of seasonality, or what I'm going to call cyclic time. And so the idea here is you can create a lookup table with a pattern that you want to repeat over and over again. And that lookup table, let's say, will only be defined on 12 months. Now you might simulate for 10 years. So we're going to create a box that generates basically the current month without worrying about the number of years. And so once it hits 12 months, it'll go back down to 0 the next year. So it constantly goes 0 to 12, 0 to 12, 0 to 12, even though your simulation time is counting up continuously in months. And so that allows us to then create this pattern where you can make it always hot in months, whatever, 6 through 9, and then cooler in other months. So how do we do that? So that's our desired thing here. So what we're going to do is, in this, I'll show you how to do this in Vensim as well. I just started an insight maker here for arbitrary reasons. You can create a variable called cyclic time. And then in the equation for cyclic time, I've got this expression here. Now, where did I get that? Well, if I look over in the sample functions here, then Insight Maker provides a bunch of time functions, which just give you a way to your simulation time. It just counts them in different units. And so I can see the seconds since the start of the simulation, the minutes since the start of the simulation, the months and the years since the start of the simulation. So it gives me all of those things. So I already can count up, let's say in months, if I want to do the seasonal pattern. Now, there's this special, so I'm going to do months, since I want this to repeat over months. Now, there's this special function called mod, short for modulo or modulus, and mod represents the remainder when you divide something by the number that comes after mod. So if I divide months by 12, it doesn't care about how many times 12 goes into it. It cares about how many months are left over. And so so the idea here is, if I give an example here, if my months climb from 0 to whatever 48, they keep climbing here. What it's going to do is, once it hits 12, 12 divided by 12 has 0 as a remainder. So this will get mapped to 0. 13 divided by 12 has 1 as a remainder, 1, and so on. So months mod 12 counts up from 0 to 11 and then restarts. And so if I fed this into a lookup table, then now I have a relative time measure of where we are in the current year, as opposed to where we are relative to the whole simulation. And this works for fractional quantities as well. So if I, months might show up as 0.5, meaning I'm halfway through the first month, and 0.5 mod 12 gives you 0.5. And if I look over here, 11.5 mod 12 also gives you 11.5, but 12.5 mod 12 has a remainder of 0.5, so it goes down to 0.5. So basically, anything mod 12 will give you numbers all the way up to 11.99999, but the instant it rolls over to 12, then it resets it back down to 0. So that allows me to create kind of I call this cyclic time, but you can also just think of this as like month of the year. So even though my months are going on forever, my months since the start of the simulation are going on forever, this keeps iterating. So what can I do with that? Well, if I go into my repeating pattern, I can create a pattern that is defined only from 0 to 12. And this could be, like I said, maybe temperature, maybe rainfall or something like that in a certain region. And so this rainfall goes up, in April, but then it comes down and there's not much rainfall at the beginning of the year, but then it comes up every April, you get average rainfall and so on. So if I combine these two things together, this is what I'm kind of showing here. Remember, I only define this from 0 to 12. If I put both of these things together and then simulate, and I look at the output of this repeating pattern, and I also looked at the output of the cyclic time, this green line is the cyclic time. Notice it resets back down to 12 when I hit 12. And when it gets piped through the lookup table, the average rain, I get this kind of rainfall patterns where I get maybe, April showers every April. So this is good because that way I don't have to draw this curve 10 times if I want to simulate 10 years. I only have to draw it once, and then this allows me to iterate over 10 different years. So that's a way we can use that modulo function to create these patterns over time. So I think I've just got a little, cyclically resets. All right, so questions about that. I'm going to show you how to do it in Insight Maker or in Vensim as well. But this commonly comes up in a lot of final projects, is the seasonality. All right, so how do we do it in Vensim? Similar sort of idea. The first thing I recommend you do is you go into model settings and you adjust your time units to be small enough to capture your repeating phenomenon. So if you want it to repeat you know, on units of months. So you want every June to be a particular temperature, then you should probably set the unit for the whole simulation to months or smaller. Don't set it to years for reasons downstream here and how we implement this in Insight or in Vensim. Then the second thing we do is we do something real similar to what we did in Insight Maker. I'm going to create a shadow variable for time, and I'm going to run it into a variable called repeating pattern. And so what do I do in repeating pattern? I'm going to make it a lookup table. So it's got the auxiliary with lookup. Now, something that I'm doing that's a little different here is the input to this variable is time, which I saw down here, but I'm going to make the input to the lookup table. I'm going to put a formula there. And this formula, modulo time 12, that's just Vensim's way of saying time mod 12. It does exactly the same thing that we did in Insight Maker, and it'll make that an input to the graph instead of time, raw time. And then I take that, I can go into my lookup table, I can draw whatever pattern I want. I make sure the pattern is defined from 0 to 12. Even though I'm simulating 4 years or 2 years or whatever, it only has to be derived or defined from 0 to 12. And then if I put everything together and I plot this repeating pattern, then sure enough, I get this pattern repeating because I simulated for 2 years, I see it repeating twice, and I didn't have to draw it twice in the lookup table. So that's how we do repeating patterns in Vensim with that modulo to cause the time to repeat. All right, so any questions about any of that? I purposely made this lecture short so that we have time at the end here in case you want to work on E2 or even start on E5. Tuesday, we're going to spend, I think, a whole lecture just giving you time to work on E5 because it's a bigger assignment. And so we don't have new material Tuesday, but we're going to kind of view it as a lab period so that, that Eric and I can help you with that assignment, both online and in person. All right, so the announcement kind of moving forward here. So continue reading the chapters. I assigned E5 today. It's not due this weekend, but it is due next weekend. What's due this weekend is assignment E2. That's what's down here. So like I said, Tuesday, we're gonna have a work day. So if you don't want it, that's fine. But otherwise, if you come here, then we can work with you on assignment E5, answer some questions. You can just try to knock it out in class. And then we've got the readings after that. Like I said, there's no other homeworks after E5. So let's do an attendance exercise. I'm happy to take questions. If you want to take off, that's fine. Otherwise, if you want to hang around, I'm also happy to help you with E2 or E5, I guess. So the attendance, I'll put the URL in the chat. And the question I have here is, what will we be doing on Tuesday? All right, yep. Use a question on that, okay. So any other big questions? Otherwise, I'll probably just stop the recording and hang out here and walk around. Again, if you don't want to work on E2 or anything, then that's all I've got for you today. And I'm going to leave the microphone on in case anybody else online needs anything. So for now, I'm going to stop the recording.